All right, this is example 10, the Atwood's machine, but we're revisiting it now. Before, when we did this problem, we did it where we assumed that the rotational inertia of the pulley was 0, and so it basically was like a massless pulley, and therefore we didn't consider that. So in this problem, we're actually now considering the fact that the pulley does have some rotational inertia in the system, so we have to also consider that. So it's a lot more complex than the way we solved it earlier. So let's get started. So the first thing I'm going to do is I'm asked to determine the acceleration of the masses. So what we're going to do is we're going to be applying Newton's second law twice, once for each of the blocks and also, well actually I guess 3 times, and then also for the pulley, rotationally speaking. So let's start off by drawing free body diagrams for M1 and M2. So I'm going to just label over here a diagram. So on M1, we're going to draw a tension up here, and we're going to draw a force of gravity going down. So we'll label this as M1G for force of gravity 1, and then this we'll call tension 1. And I've drawn the gravity going downwards a little bit bigger because the system is accelerating downwards. You can see that M1 is heavier than M2. And then on the other side, we have similar forces here. We have a tension 2, and we have a weight going down. All right, so we have FT2 and M2G. And this is accelerating upwards with the same acceleration as the other block is moving downwards. So now we're going to apply Newton's second law for this. So for the block M1, I'm going to use the sum of the forces in the y equals M1A. I'm going to consider a y-axis that's going positive downwards. So then the weight force M1G is positive, going downwards, and then the tension is the opposite direction, so we'll put that as negative. Okay, and so I'm going to eventually rewrite FT1. Let's put that by itself. It's going to be M1G minus M1A. We'll come back to this expression a little bit later on. Let's now go on to block 2. So block M2, we're going to again apply Newton's second law. Sum of forces in the y equals M2A. Now in this case, I'm going to choose the y-axis to be going upwards. So I have a tension 2 up minus the weight M2G down equals the net force of M2A. So solving for T2 individually will be equal to M2G plus M2A. All right, so these two expressions, I'm going to come back to them later. We'll call that 1, and we'll call that 2. So now what we're going to do is we're going to now look at the pulley itself. So if we consider the pulley, I'm going to draw a quick picture of that. We can draw 2 tensions on here. We have a tension FT2 or FT1 on the left side, and we have a tension FT2 on the right side. Now I've kind of tried to show that, although I may have not done the previous diagram, but FT1, all right, is actually a little bit bigger than FT2, all right, and so that this is causing this pulley to accelerate in the counterclockwise direction with an acceleration which I'll label as alpha. So now we're going to apply for the pulley, we're going to apply Newton's second law. Sum of torques equals I alpha. So in this case, we are going to look at this, and we have essentially 2 torques, and they're both actually acting at a distance of r, actually capital R, I'll label in the diagram. So we have a torque from tension 1 and a torque from tension 2 that's producing this net torque of I alpha. So that torque is, if you recall, is going to be the force of tension 1 multiplied by the radius multiplied by the sine of 90, which is just 1. Then minus tension 2 multiplied by r, again multiplied by sine 90, and that's equal to I alpha. So what we'll end up with is FT1R minus FT2R, and then we're now going to make a replacement for I. What is I? Well, we're going to assume that this is a solid disk. So if you recall back in your notes, let me just scroll up here, go back earlier, and we can see that a disk has a rotational inertia of half mr squared. So we're going to use that now. All right, so this is a half mr squared. We're also going to make a replacement of alpha. If you remember, the rotational version, remember S equals R theta, V equals R omega, and then A equals R alpha. Well, we're going to replace alpha with the tangential acceleration divided by the radius r. And that's the same r because everything's being attached at the same radius. So let's make those two substitutions. We have half mr squared, and then we have a over capital R. And then we can see some nice cancellations occurring here. So you see this r and this r will cancel out with one of these r's, and then the last r will cancel out as well. So beautifully, you don't have to worry about the radius, or everything's attached to the same radius here. So ft1 minus ft2 equals essentially half ma. And now we're going to make some replacements. We're going to substitute number 1 and number 2 into number 3. All right, so that would be, well, let's replace with this expression, all of this, we're going to replace here. And of course, all of this, we're going to replace here. Okay, so we're going to have now m1g minus m1a, all right, and then minus, let's put in brackets here, m2g plus m2a, and that's equal to our net torque of half ma. So if you get rid of the brackets, right, we'll get the following expression. And then, of course, we're going to collect like terms. We're going to bring this term and this term over to the other side. So we're going to have now m1g minus m2g equals half ma plus m1a plus m2a. And solving for a, we will get m2g minus m1, what was that? Let me double check. That's an m1g, sorry. m1g minus m2g on the top, the numerator here. And then we have 1/2 ma plus m1a plus m2. Oops, there's no a's because I've taken out an a. All right, so we get that expression in the end. So hopefully that makes sense. This is basically the total mass on the bottom, and the top is what's really the net force. Okay, so now at this point, what you would do is just plug in the values for m1 and m2, and they're given here. You've got a 15 and 10, and then you've got the mass of the pulley is 3, and the radius is 10. So go ahead and put them into the expression. Okay, making those substitutions, you're going to get that expression. And then for A, I get an answer of 1.85 meters per second squared. Okay, hopefully that's what I had down below. Yep, good. So now, last piece in question B is how would your answer change if you ignored the rotational inertia of the object? Well, essentially what will happen is T1 and T2 will be equal to each other on each side. But I think the easiest way to kind of answer that is just say, if I was 0, then this whole right side essentially would be 0, like right over here, right? This would be 0. And in the end, you would have no 1/2 m. And so you would end up, if you worked it through, all right, I'm going to try to save some time. You would end up with just basically this, m1g minus m2g, and then divided by essentially the total mass, right? The top, net force, and there's no half of m, half of that mass of the pulley. So now you reduce the denominator a little bit because there's no more mass of the pulley. And now if you plug in the numbers, you'll get the following expression, and then hopefully it's no surprise that the acceleration is going to be a little bit bigger because you're not like, having to rotate the pulley as well, and because you're assuming it has no mass. So you can obviously accelerate a little bit more. Okay, so what else is being asked? The speed at which the block would hit. This is just going back to a kinematics problem. We know that it starts at rest, and we know it falls 3 meters. So part C, we're assuming the initial velocity is 0. We're trying to find the final velocity. We know the displacement is basically 3 meters, or delta y. The acceleration, no. If you assume the pulley is massless, then it's 1.96. But I'm assuming that we're not going to consider that. We're going to consider it does have mass, and we're going to use that 1.85 meters per second squared. So then we just use kinematics. V squared equals V initial squared plus 2a delta x. The initial speed is 0. V squared equals 2 times 1.85 times 3. And then so V would be the square root of all that, which gives you an answer of 3.33 meters per second. Interestingly, later on, when we get into energy, working energy, there's another way of solving this problem using the fact that there's potential energy lost and then kinetic energy gained. and rotational energy as well. We'll probably revisit this problem, actually, and discuss how you could solve it using an energy method. All right, that's it for this example.